Welcome everybody to the UCSD Library's Climate Series in honor of Earth Month. Thank you. My name is Amy Boutros. I'm the UCSD Library's librarian for Earth and Marine Sciences and liaison librarian for Scripps Institution of Oceanography. Today I have the distinct pleasure of introducing Professor Richard Somerville. Richard Somerville is a distinguished professor emeritus at Scripps Institution of Oceanography, UCSD. He has been a professor at Scripps since 1979. He's a theoretical meteorologist and an expert on climate change. His degrees are in meteorology, bachelor's from Penn State, and PhD from New York University. He has written more than 100 peer-reviewed scientific papers. Professor Somerville is an Intergovernmental Panel on Climate Change, the IPCC, coordinating lead author. The American Meteorological Society has given him awards for both research and popular writing. And most recently, he won the 2015 Climate Communication Prize of the American Geophysical Union in recognition of his outstanding communication of science to the public and the science community. Please help me in welcoming Professor Somerville.
Well, thank you, Amy Boutros, for the very kind words and for inviting me, and my thanks to all of you for coming. So I want to cover, as you can see from this title, 3 broad topics. The first is to update you on the state of scientific research about climate change or global warming. And second, I'll cover the Paris Agreement, resulting from a remarkable 2 weeks of negotiations among virtually all the governments of the world in Paris late last year, late in 2015. And third, after those 2 topics, I want to bring the story together by explaining why I think the topic of climate change is no longer one of gloom and doom because of the Paris Agreement and other recent developments, including that public attitudes about climate change and the science of climate change are now rapidly changing. In a nutshell, the science is becoming more widely accepted. Now here's a slight modification of my title. I've added a plus sign and an equal sign, which breaks the rule that you shouldn't have any mathematics in public talks. But it does convey more about what I want to say. I would say that it's the combination of robust scientific information and wise policy decisions in Paris, informed by that scientific information, that may well enable the world to avoid some of the most dangerous aspects of climate change and possibly limit climate change to tolerable amounts to which we can adapt. In fact, I personally think that one is now justified in being guardedly optimistic. And as I tell this story, I'm going to cite several websites that you're welcome to write down that provide much more information than I can touch on in this brief talk. So here are the first 2, my own site, and the one climatecommunication.org, which is run by Susan Joy Hassel, an expert in communication with whom I've partnered for 25 plus years in helping scientists do better at communicating, helping journalists do better at talking to scientists, and so on. And if you want to see a really good TEDx talk about climate change, there's one by Susan Hassel on the climatecommunication.org site. The story that I want to tell you isn't entirely recent. It begins a long time ago. For me, it begins in 1861, more than 150 years ago. And John Tyndall, this stern-looking fellow here, was an Irish person who worked in England, in London, for his whole career. He was one of the most eminent experimental physicists of his time. Those of you who are scientists, he succeeded Michael Faraday as director of the Royal Institution in London, where he did most of his work. And he was the first, I think, to put the concept of the greenhouse effect on a firm scientific foundation. Everybody understands the basics of the greenhouse effect. Today, there are gases in the atmosphere that are transparent and let sunlight in. That's where the climate system gets its energy. But they're partly opaque to the infrared energy that the Earth gives off. And so they keep the Earth warmer than it would otherwise be. We have a natural greenhouse effect that keeps the planet habitable. And the concern today about climate change or global warming is that we are strengthening that greenhouse effect inadvertently by adding carbon dioxide and other substances to the atmosphere that thicken the blanket, that trap more heat. And in Tyndall's day, I think the greenhouse effect was as mysterious as, say, dark matter is today. And he, as I said, made the first empirical advances. He was seeking the cause of ice ages. And he immediately realized from his experiments the potential implications of his discoveries for climate change. This is a picture, a very accurate picture. I've seen the original equipment of the laboratory setup that Tyndall had. He would carefully measure the relative ability of water vapor, carbon dioxide, and other atmospheric gases to absorb infrared energy. And he found that the gases that make up nearly all of the atmosphere, which are nitrogen and oxygen, had no role in the greenhouse effect. They don't trap heat at all. The heat trapping comes from gases like water vapor and carbon dioxide, and they're such powerful absorbers of infrared energy that even slight changes in the amounts of them in the atmosphere could well produce major changes in climate. And Tyndall realized this right away. The other person, I think, that in many ways is a scientific kinsfolk of Tyndall is Charles David Keeling, whom I suspect some of you may have met. I knew Dave Keeling very well for the last 25 years of his life. He spent virtually his whole career at Scripps Institution of Oceanography. And the discovery that the concentration, which is jargon for amount, of carbon dioxide in the Earth's atmosphere is rising was made by Keeling, based on a series of extremely accurate measurements beginning in 1958, continuing to the end of his life in 2005, and continued now by other scientists, including at Scripps his son, Ralph Keeling, who's a professor at Scripps. Dave Keeling designed and built his own apparatus, just like Tyndall. His instrument was the first one ever to measure amounts of carbon dioxide in the atmosphere accurately. And he began his measurements of CO2 in two places, in Antarctica and the Mauna Loa Observatory in Hawaii, which is on the side of a volcano there. It's pictured on the right. And the Mauna Loa record of CO2 measurements began in 1958. Keeling was a young scientist, still in his 20s, and quickly yielded important new results. First, CO2 amounts rose year after year. And at the lower left there, you can see the chart of the first few years of measurements, and you can see the upward trend. And there was also, as you can see, a seasonal cycle. CO2 concentrations were largest in northern spring, when most plants begin to grow, drawing down the CO2 amount in the atmosphere. They respire in the fall, and the amount goes back up. And it follows the northern hemisphere seasons because most of the land, hence most of the plants, is in the northern hemisphere. The southern hemisphere is mostly ocean. So Keeling discovered all this. He ascribed the seasonal cycle correctly. And he also found out that the cause was entirely human caused. That the CO2 was going up not because of any natural fluctuation, but because humanity was adding CO2 to the atmosphere. And the chemical evidence for that is very convincing, that CO2 doesn't come from volcanoes or any other natural source. The dominant source is fossil fuel combustion, and there's also other sources like land use changes, mainly deforestation. Here's what that curve looks like today. And as you can see at the top left, I updated it just a few days ago. It's online, so if you're curious about what it is doing day by day, you can see. And as you can see, the numbers that were 315 or so at the lower left when Keeling began his measurements, 315 parts per million by volume, which is equivalent to molecules per million molecules. So in 1958, if you took a million randomly chosen air molecules, 315 of them would be carbon dioxide. It's about the same all over the world because the wind mixes the CO2 around. It has plenty of time because the CO2 lasts in the atmosphere a long time. And at the upper right, you can see it's now over 400. And actually, we know what it was in the 1800s before it started rising significantly, because we found air trapped in ice that it can be cored and drilled, dated, brought up, analyzed in a lab. And in these units, in that time, pre-industrial concentration was around 280. So if you do the arithmetic, more than 40% higher today than it was back in pre-industrial times because of human causes. And then you'd expect the world to warm. We have a lot of theory and modeling saying how much, but that's the bedrock data that every treatment of global warming or climate change explicitly or tacitly refers to. It was Keeling who showed that humanity was changing the chemical composition of the atmosphere. Tyndall had said CO2 traps heat, and Keeling had said the amount of CO2 is going up in the atmosphere. So in a sense, everything else is filling in the details. How much warming do we get, and what are the climatic consequences of that warming? This curve is now known universally as the Keeling Curve. It's one of the most important single graphs in all of Earth science. It's important, incidentally, to realize that these measurements, which are now sustained by an international cooperation measuring at many sites, were originally made simply because of the dedication and perseverance and skill of one scientist. The first question you might ask is, has the world warmed in recent decades? Very sensible question, and the answer is an emphatic yes. It's unequivocal in the language of the Intergovernmental Panel of Climate Change. Here's the global average temperature, in this case binned by decades. Red on the right in recent decades is warmer than the long-term mean, and blue on the left is colder. So it's clear right away that it's warming. I'm showing you a decadal averages rather than individual years because there's a lot of upside-down noise due to individual years because of natural factors like El Nino and La Nina. But the instrumental record goes back to sometime in the late 1800s. Before that, you didn't really have enough thermometers sited in enough places and calibrated accurately enough to compile a meaningful global average. You have to rely on proxy data like tree rings. But the instrumental record with real thermometers started then and continues till now. And as you can see from the language there, the 1980s were the warmest decade on record at that time, as you can see from the graph. But in the 1990s, every year was warmer than the 1980s average. And in the first decade of the current century, every year was warmer than the 1990s average. And we don't have enough years yet for me to put another decade on, but 2015 is the warmest year on record, and it's succeeded 2014, which is the warmest year on record. So it's clearly warming. There's simply no doubt about that. If anybody tells you that it paused and hasn't been warming at all since 1998, there's all this sort of pretty clear evidence that they're mistaken. There's a lot of evidence besides temperature measurements in the atmosphere of global warming. And it's not a thin chain or a thin thread of evidence, it's a thick rope. And on this picture, the white arrows pointing up show increasing trends, and the black arrows pointing down show decreasing trends. So you can see that air and ocean temperatures are both rising. So is sea level. Sea level rises because the water expands when it gets warm. Also, as ice melts on land, more of the liquid water flows into the ocean. Air and ocean temperatures are rising, sea level is rising, water vapor in the air is rising. That's because warm air holds more water than cold air. And we measure that the water vapor content is rising. But glaciers and ice sheets and snow cover and Arctic sea ice are all shrinking. So all of these are signs of a warming world. And quantitatively, they're very compelling. So for example, most of the heat, upwards of 90% of the heat gained by the climate system in recent decades is stored in the ocean, which has a huge heat capacity. 90-odd% is in the ocean. And we recently have acquired the ability to monitor the ocean much better than we'd ever done before by autonomous floats. Scripps has had a big hand in organizing that. And so we now can clearly see the world is warming by many, many different chains of evidence. At the same time, we scientists have kept careful track of how well our predictions or projections made with computer models match the climate system and its actual changes. So what I'm showing you here are results from a paper published in 2007, nearly 10 years ago, in which a group of us compared actual measured changes from 1990 to 2006. 1990 is in the middle there, as you can see from the chart at the bottom, 2006 on the right, early 1970s on the left. And we're comparing the forecasts made by models assessed by the Intergovernmental Panel on Climate Change, IPCC, about which I'll say much more soon. The top graph is carbon dioxide amount. And you can see the characteristic wiggles of the Keeling curve. And the mean of those wiggles, the amount of carbon dioxide, has increased in a way very similar to what the prediction would have showed. The middle is temperature change. And again, the line you can see the ups and downs, again, due to natural factors like El Ninos. But the range of the IPCC projections in the middle graph is the gray area on the right-hand side. And once again, the average upward trend, letting out the quasi-random effects of natural factors, is well forecast. However, at the bottom you see sea level rise, which had been measured by tide gauges, essentially floats. There's one at the end of the pier at Scripps Institution of Oceanography. That's the red part of the bottom graph. That's now been superseded by satellite altimetry. The technology is so slick that an altimeter on the satellite can measure sea level height. And as you can see, if you're close enough to look at the details there, the sea level has been rising at the very top end of the projections of the IPCC. And in fact, I think it's fair to say in general that each successive IPCC assessment raises the forecast of what sea level rise would do. Well, that's important. And here's a dramatic photograph to illustrate the importance of it, because think, for example, about what happens when a strong storm like a hurricane makes landfall. Well, the damage gets done by flooding, both flooding from the ocean, the storm surge, which is more likely to be large if the sea level is higher, and flooding from freshwater, from heavy rainfall, and there'll be more of that if water vapor is higher. That is, if the water vapor content of the atmosphere is increased. So there's more potential for damage from a landfalling hurricane because of climate change. And for that reason, my co-authors and I put on that 2007 paper this warning that previous projections, as summarized by the IPCC, have not exaggerated, but may in some respects even have underestimated the change, in particular for sea level. We said that addressed to those who have claimed in the past that IPCC exaggerates climate change or paints unduly grim future scenarios. And unfortunately, this isn't true. The real climate system is changing as fast, or in some respects even faster, than expected by IPCC. This figure shows estimated on the left and observed in the middle and projected on the right possible amounts of sea level rise from 1800 to 2100 relative to 2000, which is taken as 0 here. And the units are in feet. This is from the US National Climate Assessment, which cleverly makes measurements not in units unfamiliar to Americans, but in familiar ones, pounds, feet, miles. And you can see here that the future scenarios, look to the far right at 2100, ranged from 2/3 of a foot out to more than a foot and 6.5 feet in 2100. And these extreme scenarios are not based entirely on climate model simulations, but rather reflect a range of possible scenarios based on other kinds of scientific studies. The orange line at the far right, from 1 to 4 feet, shows the currently projected range of sea level rise, which falls within the larger risk-based scenario range. This large projected range reflects uncertainty. We don't know answers to questions, some of the questions that we want to answer, as precisely as we'd like to. So there's some scientific uncertainty. It doesn't mean ignorance or incompetence. It just means that these are difficult questions that have not yet been fully dealt with by the research. And so we don't really understand everything about how glaciers and ice sheets will react to the warming ocean, the warming atmosphere, changing winds, changing currents, and so on. There's some very recent research, not on this graph, that has suggested that 6 feet or more is more likely by 2100 than we had thought. And it's early days now, so we'll see whether that pans out. Many of our predictions have already come true, and some aspects of climate change, as I've tried to stress, have happened even faster than we predicted. So here's an example, a very graphic example of something we don't yet understand well. The Arctic sea ice extent is a minimum every year in September. That's the end of the ice melting season before the ice starts to regrow as the temperature drops. This September minimum has shrunk in recent years, and we underestimated how rapidly this annual minimum would shrink as the years go by. So you see here, in a typical recent year, on the right, that's from 2012, it's only half what it typically was in the years before 2000, shown on the left, which is 1984. So there's a drop in the Arctic sea ice extent by 50% or so, and the thickness of the ice is also reduced, so the volume of the ice is decreasing even more. There are feedbacks from changes like this. This darkens the Arctic, when sea ice disappears, so less sunlight is reflected away, more is absorbed. So in the season when the sun shines, there's more warming than there would otherwise be. It's as though you had your house wired funny, so that when it became warm, you turned on the furnace instead of the air conditioner. The computer models give us projections, and here are projected changes in North America late in the present century in precipitation for the 4 seasons, assuming that emissions will continue to increase, emissions of the heat-trapping gases like CO2. On this map, green is wetter, brown is drier. Hatching shows where models agree and changes are most significant. And in general, wet regions will become wetter, such as the northern US in winter, the top left picture. At the same time, dry regions will become drier, such as the southwestern US in spring, as you see in the right-hand top picture. Now, I don't have to tell you that the American West is already arid, and further drying brings many risks, including reduced agricultural productivity, more competition and stress between rural and urban users, and greater wildfire danger. Thus, the extreme drought that California is still in may be a foretaste of the future. Southern California, as you know, imports much of its water from Sierra snowpack and from the Colorado River, and both these water sources are shrinking in a warming climate. Our computer models predict that in the future, more precipitation will fall in heavy precipitation events than in the past. You might say we'll see more rain in downpours than in drizzles. And obviously that increases the potential for damage from flooding, and recent observations indicate that this trend has already begun. So these are observations showing the percent changes over a period of recent years in the amount of precipitation falling in very heavy events, the heaviest 1% of precipitation events for each region. And there's a clear national trend. All the numbers here are positive, except for Hawaii in the lower left. But a greater amount of precipitation is being concentrated in very heavy events, particularly, as you can see here in the dark blue colors, in the Northeast and the upper Midwest. Now, the biggest unknown in what will happen in the future is human behavior. And it all depends on what the world does or doesn't do. So different amounts of heat-trapping gases released into the atmosphere by human activities, like burning fossil fuels, produce different projected increases in temperature. And here you see a red and a blue line, which are the central values, and a pinkish and bluish area around them, illustrating projected temperature change over the current century for 2 scenarios. So we've told the models to run themselves twice. Scenario A2 is one in which we continue the ways of our past. We generate more energy by burning more fossil fuels to serve more people. And for decreasing emissions, the B1 scenario in the blue. And you can see it makes a big difference. If you look at 2100, the central lines for the high emission scenario in the red are about twice as warm as in the low emission scenario, which are blue. And that affects the world. And for the United States, you see very similar results. So the fact is that we who are alive now have our hand on the thermostat that will control the climate of our children and grandchildren. I'll explain more about why that's as true as I said it is. Here's the warming projected late in the present century under these 2 emission scenarios, high emissions A2 on the right, low emissions B1 on the left. You can see the scale in Fahrenheit degrees at the bottom. So on the right was the US with emissions continuing to increase, and by late in the current century we get typically 7 or 8 degrees Fahrenheit more warming. And on the left, if emissions are greatly reduced, we get only 3 or 4 degrees of warming. That's an enormous difference and affects everything that's sensitive to weather and climate, especially agriculture, for example. So that's the choice we have. That is, whether we get the picture on the right or the picture on the left depends on the scenario humanity, chooses to follow in how much emissions of heat-trapping gases we put into the atmosphere. Meanwhile, as I'm about to show you, carbon dioxide is building up in the atmosphere. The Keeling Curve shows you that too. And as we'll see, the window of opportunity to make this choice will soon close. There's an urgency to this matter here that hasn't anything to do with politics. It's just the way the climate system works. And because mankind is largely dithered and procrastinated for several decades now, the science has been pretty clear for quite a while, the window is closer to closing now. It doesn't stay open indefinitely. This is a good time to take stock. I said I would tell you some websites. You'll enjoy the first one if you don't know it already. Skeptical Science, which is a website I don't have any connection with except to admire it. It's collected all the most commonly heard climate myths, and then it gives clear explanations at various educational and grade levels for why they're all wrong. So these include claims such as the world isn't really warming, the data is bad or something, or the warming is occurring but it's natural and not human caused because ice ages have come and gone before people were driving SUVs, or volcanoes produce much more carbon dioxide than humans do, so puny human activities are much too weak to compete with Mother Nature. Now I know because you're here that none of you believe these myths, but I have learned that just about everybody has an unpleasant relative or two. Call him Uncle Pete. And Uncle Pete comes to dinner now and then and spoils the mood for the whole family by making these false claims, which he found somewhere on the internet. And Skeptical Science is not only very educational and very well written, it is your absolutely key source of information for refuting Uncle Pete. The climate communication website I mentioned earlier is one I'm associated with, has many resources for learning the science and communicating it well, and there's many joint activities of its proprietor, Susan Hassel, and myself. And my own website has lots of popular articles, videos, and interviews and talks, eventually this talk, and I heartily recommend them all. Here's a nice story to tell Uncle Pete and everybody else. It's a useful metaphor. There are a lot of wonderful metaphors, and this is, I think, one that has a lot of traction. Carbon dioxide is the steroids of our climate system. What do I mean by that? Well, suppose you're watching a major professional major league game, baseball game, and the slugger at the plate, who's thought to be on performance-enhancing drugs, hits a home run. So the question you can ask is, did the steroids cause that home run? And the answer is, it's not the best question to ask. You can't say that that home run was or wasn't caused by steroids because this guy was a big league slugger when he was clean. And even with the drugs, he can still strike out now and then. But if you wait till the end of the season and you look at his statistics, you see that in this season, when he was juiced, he hit more home runs than when he was clean. So you see the effect of the drugs in the statistics, and the statistics of weather is climate. So you can't often say that a given weather event, a strong storm, for example, was or wasn't caused by climate change. But the fact is that all the strong storms today take place in an atmosphere, in a climate system that has been altered by climate change. It's warmer air, it's warmer ocean temperatures, it's higher sea levels, it's more water vapor in the atmosphere. And those are the signs of the steroids of the climate system. Well, there's no silver bullet for this problem, but there's lots of very effective silver buckshot. And it starts with the low-hanging fruit, which often has negative cost. It saves money, energy efficiency, and energy conservation. But then after that, the key is renewables, much more use of sun and wind and water. And one of the encouraging things that's happened in recent years is that these renewable resources that are already widely available and are cost competitive now with fossil fuels, and their costs are often dropping rapidly. So the objection isn't a technological objection. The solutions are out there. The objection has been, until at least recently, that we've lacked the political will to act. And I think this may be changing now, so that's one reason I'm optimistic. But I don't want anybody to take a kind of Pollyanna-ish, relax, everything's going to be okay, no worries attitude from what I have to say. The threat of dangerous and potentially catastrophic climate change has not yet gone away. The climate system contains tipping points, which are thresholds, and some of which we know and some of which we surely don't know, that once passed can produce strong effects that may be irreversible. And here's one. Here's a prediction made about 40 years ago. if the global consumption of fossil fuels, this is an eminent glaciologist of that time, continues to grow, CO2 content can double in about 50 years. And if that happens, that warming caused by the extra CO2 could start rapid deglaciation of West Antarctica, leading to a 5-meter rise in sea level. So a meter for you non-metric folks is about 3 feet. So that's a 15, 16-foot rise. And Mercer's comment was in the scientific literature. All the glaciologists know about it. And now we find in recent work that this may have begun already. What you're looking at here in the big colorful picture is a small section of West Antarctica. On the little inset map at the lower left of Antarctica, you can see where it is. It's on the west coast of Antarctica, below the Antarctic Peninsula, which juts up toward South America. And what you're looking at here is a number of glaciers. You can see the spatial scale, 50 kilometers at the bottom. These things are big. The Amundsen Sea sector, which is what this is, of West Antarctica, is almost as big as France. There are 6 glaciers which drain it. Ice moves, you know. The 2 largest ones are Pine Island Glacier, which you can see at the top there, which is 30 kilometers wide, and Thwaites Glacier, which is 100 kilometers wide, and kilometers about 0.6 of a mile. And these stretch for over 500 kilometers. Ice sheets move, and these have sped up dramatically in recent years. They can be tracked from satellites. And the research results indicate a progressive collapse of ice sheets in this area. This is not a collapse that was going to occur tomorrow afternoon. It may take centuries. But once started, our best understanding is that, as in the prediction I showed you, it keeps going. There's no stopping it once it has started. So a large fraction of the ice in this basin may be gone in 200 years, and it's possible, and perhaps even likely, that the rate of retreat of the ice will increase in the future. This is excerpts from an announcement by this team of scientists, which is headed by Eric Rignot, who's at the Jet Propulsion Laboratory at Caltech and at UC Irvine, who has said, this collapse is unstoppable once it has begun, so sea levels will eventually rise 1 meter, about 3 feet, worldwide, simply from this region. And furthermore, it's likely that collapse of this sector will trigger the collapse of the rest of the West Antarctic ice sheet, which over a period of centuries will play out, and sea level will ultimately rise 3 to 5 meters more. Well, that's serious. That implies enormous consequences. The coastal cities worldwide will become uninhabitable if that happens. Once again, it's not going to happen tomorrow morning. We're looking ahead. Furthermore, it's brand new research, so I can't promise you that faults in this research won't be found or that other advances won't be made. And so this is brand new, but these people are serious and well-regarded scientists. And so here's an example of a threshold that is more likely to have been passed, as are other thresholds, the more warming we allow. So it's a warning sign that the climate system isn't always gradual, but you reach points where changes occur abruptly. And in fact, we know from the geological record that abrupt climate changes have occurred in the distant past. So the world is dependent on fossil fuels. And if you think of climate scientists as planetary physicians, which I think is a nice comparison, their advice is clear. It's necessary to end this dependence as soon as possible. And to limit global warming to moderate levels, the straightforward route is to drastically reduce our emissions of the heat-trapping gases that come mainly from burning fossil fuels. You can think of other things to do. You could hope to invent a machine that removes carbon dioxide from the atmosphere, but nothing that does that effectively and affordably at scale has happened yet. You could dream up geoengineering schemes, all of which are risky and ethically questionable and are likely to have unintended consequences. So the straightforward way to limit climate change is simply to wean the world from its dependence on fossil fuels. I've mentioned the IPCC, the Intergovernmental Panel on Climate Change. It's sometimes called the UN panel, especially by people who don't think well of the UN, but it's actually a very small agency with no budget that just organizes groups of scientists from all over the world who produce a gigantic report about every 6 years. There have been 5 of them so far. I'm an IPCC author. And these reports are non-political. They summarize and assess the published scientific peer-reviewed research in a way that is relevant to policymakers but not prescriptive of policy. So the IPCC is not an activist or advocacy organization. It doesn't tell the world to build nuclear plants or not to build nuclear plants or anything else. It just summarizes the scientific research where there's a clear body of robust science and that the science appears to have settled in, then it says so. Where there are issues that are open, it says that, and so on. There are 3 IPCC working groups, and today I'm speaking only about one called Working Group 1, which deals with the physical climate system. The other 2 are concerned with mitigation of climate change and of adaptation and impacts of climate change. The most recent such report came out in 2014, and the Working Group 1, the Physical Science report, is 1,500 pages of very difficult reading. I give IPCC an A+ for science assessment and a gentleman's C for communication. There's a lot of jargon. There's also, since nobody will read the 1,500 pages, a 27-page summary for policymakers. And that's an interesting document because it's drafted by the scientists, but is then put before the governments. That's the I, intergovernmental in IPCC. And at a very formal session with formal policy, parliamentary procedure, and with simultaneous interpretation in the 5 UN languages, the governments approve, negotiate every single word in that 27-page document. And unanimity is the rule. If a single government objects to a single word, it doesn't get into the report. So what you see is a document that your government has signed on to. And as a big favor to you, I have condensed this summary for policymakers, 27 pages of it, down to 12 points which all fit on one slide. Now, my summary is unofficial. It's not sanctioned by IPCC or anybody else. It's just my own professional judgment, but I think it's accurate enough for our purposes here. And here it is. And of course, there's much that can be said of each of these points, and we've already talked about some of them. It is warming. That's unequivocal. A lot of evidence for us. It is human-caused. We can rule out the natural causes quantitatively. So, for example, we know why ice ages come and go. Tyndall didn't, but they're triggered by changes in the Earth's orbit around the sun. And then once they're initiated, or glaciation or deglaciation, carbon dioxide is either reduced or increased in the atmosphere by natural processes, which augments or feeds back on the warming or cooling. But these changes in the Earth's orbit are important on the timescales of ice ages, 10,000, 100,000 years, but they have no power to influence something on a short time scale like the few decades that we've been experiencing global warming. Similarly, the sun can change its luminosity. It can add all the energy in the climate system comes from the sun, but we know that the sun is not changing rapidly enough, and if we convert its effect on the climate system over these decades, it's much, much smaller than that of CO2. So we can rule out the natural factors quantitatively. It's a bit of a scientific detective work. I think it's akin to the way wildfire experts can go in after a wildfire and determine whether the source of it was natural, lightning strike, for example, or whether it was human-caused, a careless campfire or arson. And we can do the same kind of thing with climate change. There's a whole branch of climate science called detection and attribution, detecting unnatural changes and attributing them to causes. And that work's been done, and the IPCC has assessed it in great detail. So when we say that we humans are the predominant cause of climate change, I mean, that's a striking statement, and many people it's counterintuitive, you know. Why can puny humanity take over from nature and become the dominant factor in climate change? But it's a fact. Furthermore, it hasn't stopped. As I've mentioned, I said the heat is mainly in the sea. Sea level is rising. Ice on land and in the ocean is shrinking. Incidentally, the evil twin, as it's been called, of global warming is ocean acidification. The ocean chemically is dilute carbonic acid, and it's becoming less dilute and more acidic as the ocean absorbs some of the CO2 that we put in the atmosphere. As I said, CO2 in the atmosphere, its amount or concentration is up 40% since the 1800s. It's now the highest, it says here, 800,000 years, but if I were to remake this slide today, which I should have, I think it's millions of years. And then 2 important points. Cumulative emissions set the warming, okay? The amount of warming you get is due to the total emissions because the climate reacts to the total amount of CO2, and much of the carbon dioxide that we put in the atmosphere stays there for centuries. And that way it's very unlike a lot of other pollutants. A lot of other gases cause heating but have short atmospheric residence times. And that means if we stop the sources, these gases immediately start to decrease and quickly go to near zero. Methane, for example, has a lifetime in the atmosphere of about 10 years. Methane is basically natural gas, and it has many sources. And it's important to do that. It's important to reduce methane and nitrous oxide and the other short-lived heat-trapping gases. It's important to reduce the particles, soot particles, for example, that cause heating. But when you've done all that, when you've only got CO2 to worry about, CO2 becomes the 400-pound gorilla in the room, because once it's in the atmosphere, much of it stays there for centuries. There's no known way to remove large amounts of it economically. And for that reason, the climate change that we allow will last for centuries. That's the final point there. And here's a graph that illustrates that. This is the cumulative emissions set to warming. So along the bottom, you see warming amounts in Celsius degrees. So 2 degrees Celsius, which is the nearest thing we have to a target. Most governments have agreed to it. The European Union has adopted it as formal policy. So 2 degrees Celsius is 3.6 degrees Fahrenheit, warming relative to the temperature in the 1800s. That's that second bar from the left. And as you can see, that will happen when you get 1,000 gigatons. That's a lot of stuff, you know, 1,000 billion tons, a trillion tons of carbon dioxide or its equivalent. The bars shown there, the whisker-like things like a sideways letter H, are so-called error bars. My friend Susan Hassel says that when she retires, we're going to open a tavern and call it the error bar. But that's scientific jargon for a measure of the possible range. So there's considerable slack in this estimate. It could be considerably higher or lower. But there's a given amount. There's the best effort we have. It's about 1,000 gigatons. And you can see the dashed line that says emitted to date. And the slide's a few years old, so it's actually a little higher than that. We're roughly halfway toward the amount of CO2 in the atmosphere that if we had nothing but CO2 to worry about, would be halfway to the amount that would cause us 2 degrees of warming. There's been close to almost 1 degree of warming so far, by the way, because there's many other gases that we haven't eliminated yet. So the long-term climate change, you have an amount of warming that depends on the total amount of carbon dioxide emitted into the atmosphere by people, past, present, and future. And as you can see, the bars increase in size linearly going to the right, and that tells you that the warming is nearly linearly proportional to the cumulative emissions of carbon dioxide. And as I said, if we continue on our merry way, burning more and more fossil fuels to make energy, we will emit the next half in just a few more decades. And that's why drastically reducing the emissions of CO2 and bringing them to near zero well before the end of the current century is important. And it's urgent to do that. And this urgency, as I've said, has nothing to do with politics or policy. It's due to the physics and chemistry of the climate system. So we people emit the CO2. Mother Nature then changes the climate according to how much we emit. That's the nature of the game. And we can't get out of the game, and we can't change the rules. And Mother Nature bats last. So I'm nearly done now, but I want to say a few hopeful things. How should we encourage clean energy? There's many thoughtful people have advocated putting a price on fossil fuels to account for what economists call an externality, for the fact that we don't pay for the real costs that using fossil fuels impose on society, including climate change, air pollution, health effects, and so on. But climate scientists, I have to tell you, are not tax experts. We're all specialists. And you know, don't ask a cardiologist for advice on your root canal, for example. And so I think you'd be mistaken to ask me how I feel about carbon taxes or fee and rebate plans or cap and trade systems. Listen to people who are experts not on the climate system, but on taxes and energy policy, and then decide. And that brings us to Paris. I was in Paris for the whole 2 weeks, both as a journalist and as a kind of mentor to a bunch of grad students that we took who worked incredibly hard and learned a lot. The Paris meeting was called COP21. It's the conference of the parties, the 21st such meeting. The parties are all the nations of the world that signed the UN Framework Convention on Climate Change, which comes from the Rio Earth Summit in 1992. And the goal of the document is to limit man-made change to levels that are not dangerous. The definition of what dangerous was never made clear, and as I've said, the nearest thing we have to a definition today is called 2 degrees. And the essential objectives of this meeting, which were met, were to form a plan to keep temperatures below 2 degrees, and with an aspirational goal, an endeavor to keep them below 1.5 degrees, which is even harder. But 1.5 degrees was strongly lobbied for by groups such as small island nations, whose very existence is threatened by sea level rise. And to limit the amount of greenhouse gases emitted to the same levels that trees and soils and so on can absorb naturally, beginning at some point later in this century. So in other words, not to allow further increases in the amount in the atmosphere. And then to go back every 5 years or so and review progress. Look at what countries have done, try to find how they could do more, assess the development of new technology that may enable new progress. And for having some international equity in the form of rich nations providing financing to help poorer nations. And what was agreed to at Paris was bottoms up, and that each country came to Paris with its own voluntary pledge of how much it would reduce its emissions between now and about 2025 or 2030, not so far from now. And these pledges are called Intended Nationally Determined Contributions, or INDCs. And it's hard to compare them because it's some apples and oranges. They're not framed in identical terms. But here's one attempt to do so by a group that I admire and refer you to, climateinteractive.org. And what you see here are 3 possible emission scenarios between now and the end of the century. The blue one at the top is no action. That's what would happen on business as usual if there's no effort to reduce emissions. The red one is what would happen if the emissions reductions that were pledged in the INDCs were to take place. Every nation said it would did what it said it would do, nobody cheated. But then with no further reductions after 2025 or 2030 when the INDCs expire, then you get the red line, and it's progress. Instead of 4.5 degrees Celsius, or about 8 Fahrenheit, you're down to 3.5 degrees Celsius, or 6 Fahrenheit and change. But the hope is that by revisiting every few years and strengthening the commitments and doing more, we ratchet down to the successful green line at the bottom, which does meet the 2-degree target. So that's the choice that we're faced with. We have a set of plans and commitments. When all is said and done, more is often said than done, but it's a start. And it has a built-in mechanism for evaluating progress. And I think it's fair to say that virtually all countries have signed on sincerely. So I'm going to wrap up now. I think that what one does about global warming shouldn't depend on your politics. It should be about how all of us want to avoid polluting and contaminating this magnificent world, and about how to protect and preserve and clean and purify this amazing planet. Another organization called Deep Decarbonization has produced this graph showing how what you're looking at is at the bottom is the years from the present to the left onto 2050 at the right, and the countries are color-coded. So the big blue, light blue at the bottom is China. The yellowish band right above that is India. The darker blue above that is the US, and so on. And this shows one set of paths by which, if the countries followed it, the emissions of 2000 could be reduced by 50% by 2050. I think there are a lot of reasons for optimism. Some of them are here. World leaders are engaged to a degree that was not true ever before. Emissions in some sectors have begun to decline already. It's no doubt that the price of solar panels and wind turbines is getting cheaper. There's a lot more technology too. There's tremendous progress in the pipeline in batteries, for example. So renewable sources with intermittent power can still power a system when the sun doesn't shine or the wind doesn't blow. There are a lot of corporations that are now acting, and there's a lot of states and localities that are now acting. And I'm very close to the scene here in San Diego, where I think there's great progress, which in San Diego, if you hadn't noticed, has a Republican mayor. There's a lot of lack of progress in Congress, I would say, it's fair to say. And there's a politicized gridlock there that extends to climate change and many, many other topics. And I'm also encouraged, it's not on this slide, but I'm also greatly encouraged by recent polling that shows that more and more people now accept the science. And that, in fact, the tremendous partisan divide among people, with liberal Democrats accepting the science and conservative Republicans rejecting it, is weakening. And in fact, the biggest change in recent polls shows that more and more people who self-identify as conservative Republicans accept the science. And I think that's the necessary step. You start with the science, and then you bring in your politics and priorities and values and convictions to determine the best way to attack the problem. But you don't argue about the science that is competent and very convincing, I think. I highly recommend the Solutions Project. This is Mark Jacobson and others at Stanford who have done serious analysis showing how to power the entire world and this country and each state individually on wind and water and sun. It's not an easy job, but it wasn't an easy job in World War II to convert factories to building planes and ships and tanks instead of passenger cars. And it wasn't an easy job to have a Marshall Plan to rebuild Europe after the war. So it's that kind of effort. It's a huge restructuring of what the country's done. It takes a huge effort, and it's doable. The alternative of letting climate change get worse is very risky and extremely expensive. So to wrap up, here's this title again. This, I think, the robust scientific information informing wise policy decisions in Paris and the near virtual unanimity among nations in accepting the science may well enable the world to avoid some of the most dangerous aspects of climate change and possibly limit climate change to tolerable levels. In the final analysis, I think that coping with climate change is a moral and ethical issue. I suggest that at a minimum, there's an intergenerational equity consideration. We owe future generations at least a planet that is as undamaged as the one we inherited from previous generations. There's a north-south equity issue. What do we in the rich nations owe to the billions of people alive today on this earth who don't yet enjoy what all of us would consider a bare minimum of rights and privileges, access to clean water, decent health care, and the material comforts that come from a certain level of affordable energy. Our prosperity has been built on having abundant, affordable energy from fossil fuels, and we've used the atmosphere as a free dump for the waste products, which we now understand are capable of producing terrifying side effects. And finally, what do we owe to the natural world? Because one of the sure consequences of unmitigated climate change is an unprecedented level of species extinction. There's a nice quote here that I'm going to leave you with. It was from Sherry Rowland, a hero of the ozone hole controversy in the 80s, who said, "What's the use of having developed a science well enough to make predictions if you don't do anything about it, if you just stand around waiting for them to come true?" And I talked to him late in his life, and he completely agreed that this applied to global warming also. If I may close on a personal note, I've been a professor at UC San Diego for 36 years, and a very high point of that time came in 2012 when my colleague Ramanathan and I shared a stage with the Dalai Lama in front of thousands of UCSD students and faculty and staff. And it's simply wonderful when someone who is so widely admired and respected speaks out on issues like this. And the Dalai Lama has spoken out repeatedly saying that he thinks it's important for the world to find a solution to climate change. And there are many other religious leaders, notably Pope Francis, who have said that caring for the endowment, including the climate, is a duty that resonates with the concept of stewardship of God's gift to humanity. You don't have to be a Tibetan Buddhist to understand that when respected and revered spiritual leaders of the stature of the Dalai Lama speak out in these terms, they have an effect. So I'll say it one more time. This ought to be non-political. The science is international, competent, objective, nonpartisan. There aren't any liberal or conservative thermometers. There aren't any Republican or Democratic satellites. And what to do about global warming shouldn't depend on your politics. Most of the graphics that I've shown come from the most recent National Climate Assessment, which is very well written and definitive and available online. I'm grateful to the photographer Sylvia Ball Somerville, whose husband I am. All the photos that I've shown are hers, so I do have the right to show them and put them on TV. And there's a lot of financial and other support come from the sources that I have shown below. Thank you very much.